If you if you want to go ahead and pull off that prelim, it's the Green's function problem. From that, don't pull off the one with solutions. We'll go over solutions sort of subsequently. Do you have a preference? So last time we did this, we did a breakout, and then with each part, we came back to the main room. Do you prefer to do that, or would you rather just work the whole problem? Maybe break it up still? Okay. So some heads nodding and some shoulder shrugs. Okay. All right. So yeah, maybe it's a bit too long just to, work in breakout rooms the whole time. Let's keep it a little more dynamic. Okay. So I'll share screen, and then I'll also give you a link to the PDF. Maybe I should do that now. And then you will be randomly assigned to breakout rooms. We'll probably do like 3 groups again. So this is really to try and crystallize some of the concepts on using Green's functions to solve boundary value problems. And try to do this without looking in your notes, especially problem C, because you essentially just look in your notes for the answer to problem C. So part A of this problem is to essentially go from this boundary value problem for the Poisson equation with the Dirichlet boundary condition to the boundary value problem for the Green's function, and to essentially write what you need out in terms of your fundamental solution, and then anything else you need to formulate your Green's function. So actually, this one shouldn't take you too long. So maybe we'll do like 5 to 7 minutes in the breakout rooms. So let me, if you need that link to the prelim, we'll go ahead and provide that now. The prelim, and then you'll have it just in your room when we go away from this. All right, so I put the link in the chat, and now I'm going to go ahead and do breakout room. So just work part A within your breakout room group. I'll circulate again. Yeah, let's see, we have 10 people, so let's keep it to 3 per room. And yeah. Okay. I think they're pretty randomized now. All right. Okay, we'll go ahead and open the rooms. And yeah, take 5 to 7 minutes maybe. All right, does anybody from your group want to present your solution?
Everyone mutes themselves.
Or talk me through it, and I can write.
Yeah, I mean, I guess the general idea is that you want to solve a homogeneous version of your PDE, which has a singularity at x equals y, but is otherwise harmonic everywhere. So negative Laplacian of g is delta of x minus y. And the boundary condition is just 0.
Right. Yeah. So that's kind of the first part of the idea. So let's but we need to relate that to the fundamental solution.
Mhm. Yeah, so then you can plug in that relationship.
Yeah. So I think the first part of what you said is, you can do this in sort of shorthand, right? Minus the Laplacian of G is equal to delta of X minus Y on omega. And then you're saying G is equal to 0. You have to be a bit careful about this, right? So,
Right, so it'd be on the for X on the boundary and any Y in the domain.
right. As long as Y is in the domain, right? And then the second part you were saying is what G is equal to.
So G is capital Phi, so the fundamental solution minus what we call little phi. And so that tells you that, so your fundamental solution has a singularity at X equals Y. So little phi is going to be harmonic and it will have the same boundary conditions as the fundamental solution, which is G.
Right, yeah. So the way you get this is just to write this, right? So delta X minus Y. Yeah, because this and this cancel, right? Then you just end up with this on X and Y are in omega, and then right, and then phi X Y is equal to 0 on X is on the boundary, Y is anywhere inside. Okay. All right. Cool. So keep working on part B. Let's take maybe 6 minutes for that. See if you can get it in that time.
So is
right.
B trying to, is B asking us to prove it for big G or for little phi? Because I guess when I originally read A, I was thinking they were just asking for the equation in terms of big G. And I was like, well, they wouldn't have given us the form of big G if they didn't expect us to do anything with it.
Right. Well, you'll need it for C, sort of, right? But G, yeah, you wanna prove it for the Green's functions themselves.
Okay.
So yeah, show that the Green's well, the Green's function, if it exists, is unique, right? So just do your typical uniqueness proof, but for the the boundary value problem for Green's function. Okay.
So this little phi superscript X on the boundary, should that be equal to the fundamental solution on the boundary so that they cancel? Okay.
Yeah. I wrote that hastily. Right. My bad. Yes. This should equal your fundamental solution on the boundary in order for it to cancel. Right. Sorry about that. All right. Thanks for that catch. Okay, I'll reopen the rooms. Yeah. Does any group want to lead the discussion on this one?
We didn't say a lot. I mean, it might be kind of short.
Okay.
So I think from part A, you can conclude that the uniqueness of the Green's function is equivalent to the uniqueness of the solution to this boundary value problem.
Mm-hmm.
And I think that's Laplace's equation with Dirichlet boundary conditions, which you can show to be unique using the minimum maximum principle.
Yeah, that works fine.
Okay.
Yeah. I mean, you can look at the solutions too. There's a slightly different formulation, but as Sage says, you can also just treat the boundary term essentially. And then, yeah, you're not working with the singularity or anything. And then you have, you have a Laplace's equation with a homogeneous boundary condition. So max min tells you it's 0. So yeah, you essentially need, yeah, you don't even need continuity, although you needed continuity to apply the min-max principles. So you would need appropriate continuity assumptions, but everything else should be fine. All right. Let's do, so the last part is a bit longer. It sounds like some groups were already discussing it. Let's maybe take, I don't know, 12 to 15 minutes to work on the last part. And yeah, it's not far off from some of your homework problems, so it will be time well spent to work on it. All right, we'll go ahead.
When you say if those certain continuity conditions are satisfied, does that follow from the existence of, like, because that's the premise of B, or could it exist but maybe certain solutions won't satisfy those conditions? Or
Yeah, I mean, it's right. We're not being real firm there, right? So do we know that the Green's function that we get is going to be like a classical solution to the Green's function boundary value problem? Maybe it's not, right? If it exists is more, yeah, if there is a solution to this problem, right? That it's unique, but
okay.
what's hidden in there is that, yeah, in order to apply, either an energy argument or max min principle, you need some minimal conditions on continuity, which we're not really saying there, right?
Sure.
Just to be rigorous about it, keep in mind what level of continuity you need on your solutions, right? So yeah, I mean, C2 should be plenty. Yep. All right. All right, let's reopen the breakout rooms. There's my window. Okay. Okay, do you, Kyle and everybody, do you want to share your screen? Because you had kind of a nice thing written out then.
The this?
Yeah.
Okay.
All right. Do you want to talk through it?
Sure.
I guess
Or
everybody. I gotta wait for everybody to get back.
I did it last time. I don't know if someone else, Kyle or David, wants to try their hand.
Yeah, maybe Kyle was explaining it before, so maybe do you want to talk through it, Kyle?
Which one?
Kyle Weischer.
Oh.
Sure. Is everyone back?
I think so, yeah.
Okay. So basically on this one, we know it's pretty straightforward to know like the method of images on like the flat boundary and the curved boundary. So the hard part was when you look at just method image on the flat boundary, you know that the fundamental solution and like our x1 here would cancel out. But that x2 term could still give us issues. So we wanted to find a third term, which is x3 for us, that would kind of knock out the contribution from our other boundary. We're looking at one of them. And And the way we did that is we just kind of considered the circle as a whole and figure out what would cancel out on all the sides. So we just reflected over, you look at two different ways. You could think of it as kind of first reflecting from our original point, X. You can think of it kind of as first reflecting from like here, from the outside of the axis, and then reflecting outside the boundary of the circle again. Or you can kind of think of first reflecting outside of the circle and then across the boundary, and you'll get the same point. But basically, looking at what we have below, this first term is kind of contribution of x2. The second one's x1. And this third term is kind of going to be this x3 guy, which will cancel out if we're looking at like the flat part, the flat surface, that'll cancel out the contribution from the curve. And if you're looking at the curve, this x3 part should cancel out the contribution from the flat part. Yeah.
Great. Thanks. Yeah. So the general idea, and this is true anytime you have the intersection of these kind of fundamental images solutions that we've talked about. So a half space and a ball, right? So most of what you're going to see in the problems, and also if you look at prelims, right, are some variation on that, right? And so this is just a case where you have the intersection of a half space and a ball. And so you need essentially 2 to the n total, pieces in your Green's function in order to account for all of these intersections, right? So in the case where you only have one kind of, fundamental partitioning of the of Rn, then you're just going to need 2, right? You need the fundamental solution and then the reflection to the outside of the boundary of your domain. If you have the intersection of a ball and a half space, then you're going to need 4, right? The fundamental solution, the reflection outside the ball, the reflection outside the half space, and then the reflection. So the reason you have this minus sign here essentially is, as Kyle was saying, you're reflecting outside the half space and then you're reflecting outside the ball again, right? So each time you reflect, you pick up a minus sign, right? So when you feed this back into your Green's function, this last part is going to be a plus sign, right? If you had something like a quarter plane, or even in R3, you could have like the upper right octant or something like that. Upper right octant would be the intersection of 3 half planes, and so you're going to have 8 terms in your Green's function in that case. Fundamental solution, the reflection, and then reflections of reflections, and then reflections of reflections of reflections, right? So the pictures like these are really helpful when you're solving these problems because it just helps with the bookkeeping essentially. And then usually on the exam, what you are going to want to do is just show that everything works out on the boundaries. Check this boundary, the midline here, and then check the half sphere boundary there. Okay. Any last questions or comments? Sorry, I know we ran a bit over. Okay. Well, if you want to take a look at the solutions, they're easy to get to. They're on the website there. Last week of classes, we'll probably circle back and do another Green's function problem like